To this webinar, Snack and Learn webinar about WSP's Samba tool for hydraulic modeling. So just a few guidelines. At the GoToWebinar panel, you will find a chat form for questions that you can type in, and we will return to the questions after the webinar or at the end of the webinar. And also in the GoToWebinar, you will find a handout box where you can download a PDF of this presentation. So just a bit about myself. My name is Jørgen Torp Petersen. I'm the technical director of our climate adaptation and urban development department here in WSP in Copenhagen, Denmark. I am a regional physical geographer, and I've been with WSP for 10 years now in Denmark. And I'm currently heading a group of about 10 hydraulic modelers who work with climate adaptation and urban drainage, mainly stormwater, and river floodings from river and creeks. And I am also one of the developers behind the SUMBA tool, which is short for Sum of Water and Basins, along with a whole lot of colleagues, which most of them are mentioned here. So today I'm going to tell you about SUMBA, the background, why have we developed this SUMBA software tool, how does it work, and we have a few examples of case studies, and we will end with a Q&A session at the end of the webinar here. So the background is that over the last year, we have seen the demand for quick calculation based on long time series of precipitation data for very simple hydrological systems. We have done that with box models. This is especially the case for dimensioning of retention ponds. Prior to Samba, we did those kind of calculations with a spreadsheet, Excel, or with some simple programming in for example, Python or MATLAB. Here's one example from a spreadsheet where we have done those simple kind of box modeling in a spreadsheet here. And the input for those kind of calculation is, at least in Denmark, precipitation that we have measured in Denmark since 1979 on 1 minute time scales. So since 1979, we have approximately 21 million data points of recordings of precipitation at each of these approximately 200 sites in Denmark. And that's one of the reasons why we have left the spreadsheet calculations, because we simply run out of line in Excel. So the principles behind a box model is actually quite simple. I have tried to illustrate it here. At the first minute, we have precipitation over a catchment that flows into a basin or a pond with an outlet. So for the first minute, we know how much flows into this basin and how much flow out, and we can keep track of the volume in the basin. If we go to the next minute, it rains more, runs into the basin, and we have an outlet again. So we keep track of how much water we have standing in our basin here. The third minute, perhaps it doesn't rain at all, so we will have flow out of the basin, and the same in the fourth minute until the basin is completely empty. So we keep track with this simple box model of how much water flows into this retention basin and how much flow out, and the resulting volume of water in this basin. It's quite easy to understand. It's not at all rocket science, and there are some very convenient pros with those kind of box models. They're very easy to understand. They are extremely fast in the calculations. They're able to do simulations on very long time series, and they're able to correctly describe combined events. And also the water balance is always correct, which is not always the case for more advanced hydrodynamical software. And the simulation are based on historical precipitation data with very long time series. Of course, with these kind of simple models, there are also some cons or drawbacks. We have lots of data. It's really hard to make changes to the model, especially if you do it in a spreadsheet or in a Python or other kind of scripting software. It's very hard to do a proper quality control check. And we do not solve any hydrodynamic equation. We don't have any Manning numbers. We don't have any time delay, and we don't have any attenuation of discharge in those simple box models. Some of them are actually overcome with Samba. Here is a screenshot from Samba where we define the precipitation that we would like to apply to a catchment area. Here we define the catchment area. It's 10 hectare with 0.6 millimeter initial loss. And from this catchment, the water flows into a basin where we define the hypsograph. That is the relation between the level in the basin and the volume, the water level and the volume. Define that the water should flow into the basin, and then define a few outlets. Here is the normal outlet. It runs with 20 liters per second, and here is an overflow. So the model knows what to do with water if we have more volume in the basin that it can actually hold. And we have run this model for 40 years of data. That is those 21 million data points, and it returns a result within a few seconds. As we see here, this is one of the results that tells you for every minute in these 40 years long time series, how much water do we have in this basin. So some of the drawbacks or cons from these simple box models are solved with Samba. It's no problem to handle lots of data. It's not hard to make any changes to the model, and it's very easy to do a proper quality control check because we have this simple user interface in the model. We still do not solve any hydrodynamic equation. We don't have any Manning number. We don't have any time delay, but we are able to do attenuation of discharge with a time area concentration curve. So when do we use this Samba software here in Denmark? Well, here's a list and all list. We use this software when the main focus of the model is volume rather than flows. Samba is very good at keeping track of these volumes, and the flow is not described with these hydrodynamic equation. We simply move water from one retention volume to another, or storage volume to another in time steps of 1 minute. We also use Samba when we need to do simulation based on very long time series of historical precipitation, and when we have a model with several basins that are connected to each other. Also, if the basins have or ponds have more than one outlet, it's very easy to define in this software. When we need to know something about yearly balances, it's easier to use Samba than to do a job list in, for example, MyUrban. And also when evapotranspiration is important, we can put that into our Samba model as well. If we want to implement climate change to the precipitation, we're able to calculate the return periods of individual rain events in this precipitation time series, and then apply a climate change factor to every single rain event, depending on the return period. We also use Samba when high temporal resolution is more important than a correct hydrodynamic description. And when we need to know something about concentrations of solute and purification, we're able to put that into the model as well. And also we use this model for very fast screenings or scenarios that we will later detail or verify with a fully dynamic hydrodynamic model, for example, MyUrban. So Samba is actually built up in what we call the Lego brick system. We have a number of Lego bricks that we can connect in different ways. And as you saw before, we just draw these Lego bricks and connect them in different ways. And we have a lot of bricks in our toolbox. The top right one are all the time series that we can implement: precipitation or climate changed precipitation, discharge in a river, evaporation. We can put in time series of water levels, Manning number, or even some cyclic daily data, for example, for precipitation, if we would like that. We can define the catchment and define different kind of basins, whether they are dry or whether they have a permanent volume of water in them. And we can define flow between the catchments and basins. Those are all the purple boxes. The outlet, either a simple outlet with a steady flow, or an outlet depending on the water level in the basin, QH outlet. You can also put in these evapotranspiration outlet, and also more sophisticated outlets where we base the flow between basins on the water level in 2 or more basins. We're able to manipulate flows in time series with a flow transformer. For example, there's time area concentration curves. We can sum flows if we like that. We can do transformation to our precipitation on a monthly basis, for example. And we can tell the model where it should put water into a basin in all the summer months and in another basin in the winter months, for example. And also we have a number of toolbox at the lower right hand that defines solute concentrations and how they can be removed from the system by either first order degradation or depending on the flow rate in, for example, a SETI pipe. So here's one case for a very simple retention basin in the northern part of Denmark. We have the precipitation that rains onto a catchment, which is approximately 1 hectare, and the basin is 500 cubic meter large. There has an outlet of 1 liter per second. It's located here in the real life. And what the client would like to know in this case is, how often does this basin overflow? So we build a model, put in our precipitation, and calculate for approximately 40 years of 1 minute precipitation rates or intensities, and we get from each minute how much water is actually in the basin. And as you can see here in the middle part, we have more volume in the basin that the basin actually can hold, more than 500 cubic meter, which returns in an overflow. And afterwards, we can do in the Samba software some simple statistics on the overflow. In this case, we have 12 overflow in approximately 40 years, which gives us a return period for overflow at approximately 3.35 year return rate. Here's another case, pretty much the same basic model, but in this case, we also include the evapotranspiration from the model. We have a time series of potential evapotranspiration millimeter per day. And the client would like to know, will this retention basin run dry during summer? So we run the model with the evapotranspiration and precipitation and catchment area and so on. And we can see in the very dry summer, the water level falls approximately 20 centimeter. So if the client would like a minimum water depth of 1 meter, then we should locate the outlet of the basin 1.2 meter above the bed level in this basin. So this was a very simple model that we could set up in half an hour and so, and return a good answer to the question in almost no time. Here's a third case study with curb extension from the city of Copenhagen. It's an infiltration element with an overflow to the combined sewer. Water runs from the street into this vegetated curb extension, and beneath that we have first of all a filter soil that rinses the water, and below that we have these storage volumes for skeins with an overflow to the sewer system, as we see here. And the client would like to know how much water is actually infiltrated if we build this model in real life. We can build the model here with, we have in this case 3 different retention volumes. The top layer of the curb extension itself, the filter soil, which is also defined as a volume here, and finally the detention or retention volume beneath the filter soil with an overflow to the sewer system is here, and here you see the overflow to the sewer system here. So it's quite easily to run this model also with evapotranspiration from the vegetation, and we could see if we have a yearly precipitation of approximately 566 millimeter per year, then 20% is lost to this initial loss with 0.6 millimeter per rain event. Approximately 40% is infiltrated, 3% is evaporated, and 38% is discharged to the sewer system. And we could also tell the client that this bypass of the filter soil amounts to approximately 3% of the total water that runs into this system. So this water may infiltrate without cleaning first. Here's a fourth case study. This is the cleaning efficiency of a combined purification system with infiltration and a normal purification pond. The system today looks like this. We have a bed volume here, which is very much under-dimensioned according to the Danish BAT standard, which is 250 cubic meter purification volume per hectare of impervious area. Here we have approximately 40 cubic meter of retention volume. So this system is supplemented with an infiltration basin that will be located here. And the client would like to know if this combined system with a small purification pond combined with an infiltration pond is as efficient at cleaning as the normal Danish standard would demand. So we build the model here in Samba. We add some solutes here, nitrogen, phosphorus, and suspended solids into the system here, and they are removed with a first order degradation here in our bed volume, and with a new concentration in the water that has infiltrated from our infiltration pond here. And after we have run the model here, we can calculate the cleaning efficiency of this combined system, and compared to the Danish standard bed that you see here at the bottom, we can see that this system is more efficient at cleaning both for phosphorus, nitrogen, and suspended solids compared to the normal Danish bed system. Here's a final case study that I have chosen to show you today. This is a very big SUMBA model, and it's just to show you that these SUMBA model does not need to be simple. They can also be quite complicated. This is from a city in Denmark that holds approximately 40,000 people, and this is the total sewage system with all the retention volume located in this sewage system. It's an ongoing research project that we have now for the utility company, where we try to optimize the system by regulating the flow between these different storage volume in the system in order to make best volume of the total retention volume that we have available, so that one basin will not overflow while we still have available volume in another basin, another place in the system. So how should we regulate the system in order to make best use of the total retention volume? I don't have any results from this. It's ongoing now, but it's just to show you that we can also do some quite complicated tasks or scenarios with the Samba model. And this is definitely one of the scenarios that we will, when we have done all the scenarios that we can run really fast in the Samba tool here, we will take our regulating system into a more complicated model, MyGurbel model, and then do a verification of the Samba model afterwards with a complicated model that will probably run for a day or two in the MyGurbel software, but we can do this scenarios calculation in a few minutes. So we're able to do lots of scenarios and figure out how should we control this system, and then verify it afterwards with a model that is quite that takes a long time to run, so long that we don't do any scenarios with that model. So do you think Samba is for you? Well, it could be for you if you would like to do some simulation based on very long time precipitation data. And of course, if you have reliable, especially precipitation data with a high temporal resolution, then Samba might be a tool for you that you can implement in your projects. It is a tool that we have developed here in WSP Denmark, and if you are a WSP employee, you're welcome to use this tool for free. We have to figure out how you can get access to it, but it should be no problem. Just write me an email and we will find a solution to you, and we can even give you a short introduction to how this software works. So, Sharon, do we have any questions?
Thank you, Jon, for your presentation. So just before we move into the Q&A period, I would like to remind attendees you can enter your questions in the question box on the GoToWebinar platform, and also the presentation is available to download as a PDF in the handout box. I will start with the first question. Is it possible to use precipitation data with a lower time resolution, for example, days?
Yes, it is possible. As I mentioned, in Denmark, we have very long time series of precipitation, very high reliability, and also with a very high temporal resolution of 1 minute. But if you have precipitation data with, for example, 1 hour, then we could easily implement that into the Samba tool, the Samba software. It will still run in 1 minute time steps, but it will just even out the 1 hour data to 1 minute rain intensity. You can also use a daily precipitation rate, but for lots of application, you need precipitation data with a higher temporal resolution. But absolutely, it is possible.
Thank you. Are there any plans to translate the software into English?
Currently, no, but it's quite easy to use the software. It doesn't have lots of word built in. We have a colleague in Poland that actually works for our department here in Denmark, but he's located in Poland and doesn't speak Danish at all. And he uses this Samba tool on a regular basis. And just with Google Translate or with a quick introduction, he was able to manage to use the software without any problem. It's not that it's pretty self-explanatory, but if you have any questions with the software, of course you can ask us, and otherwise you will get really far with Google Translate. And of course, if it turns out that there is a high demand from WSP across the globe, then we will later on translate the software into English, for example.
Thank you. Can the tool be used in larger river systems? I have a name here. I'm not sure I'm pronouncing it correctly. Konginen? I send it to you for you to review the name.
Yeah, that's yeah, we can. We have used a Samba tool for rivers in Denmark. Of course, we don't have any large rivers in Denmark, but we have used the Samba tool to both. There is a statistical package in the Samba tool where you can do return periods of flow in your river system, and then you can, for example, let basins with different kind of outlets run into to the tool and then do some statistics on the resulting flow in the river system. The tool does not calculate any water levels in the river. It only routes the flow. So you will have to calculate the water levels afterwards with some kind of QH relation from the river.
Thank you. Can Samba be used for mapping of floodings, like a Mike 21 model?
Not directly. It doesn't have a digital terrain model built in, but we have used it indirectly for these kind of overflows from basins. We know how much overflow we will have from this basin, and then we can afterwards put this volume into a terrain model and see which kind of area is then flooded with this volume of water that runs that is overflown from the basin. But it's a post-processing of the data that you can get out of the Samba model.
Thank you. How, in your opinion, do the clients benefit from Samba?
They can benefit in several ways. First of all, we are able to answer some questions with Samba, for example, about purification and concentrations of solutes that we were not able to answer before we had the Samba model. So we can answer questions that we were not able to answer before. We can also answer questions that we were able to answer before, but we can do it a lot faster and more reliable than we could, for example, with a Mike 21 model.
Thank you. Is there a user manual for the tool?
Not yet, but that's one of the things that we have in pipeline. And again, depending on the demand for the software, we could write a manual, and we would of course then write it in English. But at the present, there are lots of presentations, and some of these presentations actually functions as a manual that my colleagues here in Denmark uses a lot.
Fantastic. We don't have additional questions, so we are at the end of our webinar session. Thank you, Jon, for a fantastic presentation, and thank you everyone for attending the webinar today. We look forward to seeing you in our upcoming webinars, and you can follow up directly with Jon via the contact detail shown on the screen for any additional questions. So thanks again, everyone, for your time.
Yeah, thank you very much for listening. Goodbye.